Oh, hello, 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 hello. So, hi everyone. My name is Dilshad Raja, and I am here to discuss today's Codeforces contest 1073. That was a Div1 plus Div2 round. Okay, a separate Div1 and a separate Div2 round. So it happened yesterday. So let's discuss the question. So let's start with Div2 A's problem. Okay, so Div2's A problem. Let's read the question. So we have n cards arranged in a row. The ith card has an integer AI written on it, and all the numbers are distinct. Okay, and we have to color each car either red or blue such that some conditions are satisfied. So every two adjacent cards in the row have different colors. Okay, and if we arrange the cards so that the numbers on them are increasing order, any two adjacent cards in the new row must also have different colors. Determine if such a coloring exists or not. Right. So, uh, yeah. And the constraints on n is very nominal, like n is 100 and test cases are 200. And it is guaranteed that all the elements of A are distinct. Okay. So this distinct thing is very important actually. We just have to say reply with yes or no. So if there exists a valid coloring, then yes, otherwise no. Okay. So what are we given here? So an array, okay, and we have to assign every AI some color, okay. So if I give this number as red, then automatically this number would be blue, this number would be red, this would be blue, and so on. Okay. So there's actually no freedom given to us. Okay. The only freedom we have is either I can apply the first element as red or the first element as blue. Okay. And if I sort this array, and if I sort this array, then all the elements, like it would be B1, B2 up until Bn. If I sort this array, then again the colors should be alternating. Okay, so either it should be red, blue, or it should be blue, red. Okay, we don't know about that. So the easiest way to check this is you can notice that in the original array to have a valid coloring, the numbers at odd indices should have the same color, right? And the number at the even indices should have the same color. Okay. So I'll just I what I'll do is I'll initially mark them as 0 1 0 1 0 1. Okay. So this is going to be 0, this is going to be 1, this is going to be 0, this is going to be 1. Okay. So that gives them an alternating kind of pattern. Okay. And then what I can do is, so I can make a vector of pairs. Okay, I can make a vector of pairs. So the first element would denote the value AI, and the second element would denote 0 or 1. Okay, so then I will sort. Then I will sort this. Then I will sort this array. Okay, so since all the AIs are different, the ordering after the sorting is not really affected by the second element. It is only determined by the first element. Okay, so that sorted order. So in that order, we just have to check that the adjacent two elements should have different color. Okay, so we don't really need to specify if BI should be 0 or 1. Okay, we don't really need to check. Okay, what we can do is we can just do something like this. So the color of B2 should be different from B1 and so on. So the color of B3 should be different from B2 and so on and so forth. Okay. So if we check it like this, we don't really need to go into much details. Okay. So let's look into the implementation. So here's the code. So as I said, I have made a vector of pairs. Okay. and the first element is just my AI, and the second element is just its parity, the parity of the index. Okay, and then I'm sorting this, and I'm starting with the index one. Okay, so zero based index one, and and then I'm just checking if this element has the assigned parity equals to the previous or not. Okay, if it is equals to previous, then my answer is no. Otherwise, I'll just output my answer as yes in the end. Okay, so that's that for the first question. Overall time complexity is big O of n, and space complexity is also big O of n. Okay, let's move on to the next question. So we are given an integer a consisting of n elements. Denote f of l comma r as the MEX of the subarray of l comma r. Okay, and we have to determine if there exists a reorder of the array, that is a permutation of the array A such that for every I from 1 to n minus 1, the subarray of the prefix till ith index doesn't have the MEX value equals to the MEX value of the suffix from I plus 1 to n. Okay, yeah. So the MEX of the prefix must be different from the MEX of the suffix for every such index I. Okay, we have to determine that. Okay. Uh, so yeah, and again the constraints are not that hard, but yeah. So uh, so like let's try to think of when can we do it and when can we not. Okay. So let's say if the array doesn't have uh, the elements. Let's say the array doesn't contain zeros. Okay, doesn't contain zeros. Okay, so if it doesn't contain any zeros, then however you want to reorder it, any prefix would have MEX equals to 1, and any suffix would also have MEX equals to 1, right? So automatically the condition is not true. So the array must have zeros. So the array must have zeros. Okay. Let's say, what about, does the array should have ones or zeros and so on? Okay. Also, how about, what about the number of zeros? Can we frame any kind of condition on the number of zeros that are appearing in the array? Okay. So let's say if the number of zeros is just one. Uh, uh, let's wait for that. Let's look into how ones affect my answer. Okay. So if let's say there are no ones, let's say there are no ones, then how is it going to affect? So uh, so how is it going to affect, right? So let's say I have two zeros and two ones. Like, what is the best way to order them? Should I order like something like this, 0101? Is it a good thing? Is this a good way to order? Okay. So if I order like 0101, then there exists this partition for which the MX would be 2, and for this as well, MX would be 2. Okay. So the best way to order this is I place all the ones before zeros. Okay. I place all the ones before zeros, and then I place all the zeros. Okay. So then what would happen for every subarray here? The MEX is going to be equals to 0, and for here the MEX is going to be either 1 or 2. Okay, right? Let's say my boundary reaches here. So for this one, my MEX is going to be 2, and from here my MEX is going to be 1 only, because there is no 1 here. Okay, so 1 is going to be here only. So in this way, I can reorder my elements, right? I can place all the ones before all the zeros. Okay, you can check by yourself how every partition is going to lead MEXs with two distinct values. Okay, right. But there is also one edge case. There is also one edge case that um yeah, and what about there doesn't exist any ones? What about there doesn't exist anyone? So let's say there is a 0, 0, 0, 0. Okay. So for this partition, my MEX is going to be 1. For this partition as well, my MEX is going to be 1. So in this case, it is not possible, right? But there's one edge case that if the number of zeros is equals to 1 and the number of ones is equals to 0. So there is no ones and there is only one zero. Okay. So, and after that, there is anything. So, for this partition, it is going to be MEX is equals to 1, and for this partition, the MEX is going to be equals to 0. Okay. So, if the number of zeros is exactly equals to 1 and the number of ones is exactly equals to 0, then there exists a valid ordering. Otherwise, uh, otherwise, the number of zeros has to be greater than 1 and yeah. So, if ones is equals to 0, then zeros has to be greater, then 0 has to be great is equals to is should be exactly equals to 1, and if the number of ones is greater than 0, then zeros has to be greater than 1. Okay, so this is the so yeah, this is the final solution. Let's look into the implementation. So I have made this frequency array A. So whatever element I am getting, I am just incrementing its frequency, and in the end, I am just checking if the frequency of 0 is either 0. So if the frequency of 0, then it is not possible. Otherwise, if the frequency of 0 is greater than 1, but the frequency of 1 is exactly equals to 0, right? Then only my answer is no, otherwise my answer is yes. So that's that. Uh, so the overall time complexity is big O of n. Space complexity is also big O of n, right? Let's move on to the next question. Let's move on to the Div1's question. Okay. Yeah. So let's read the first question of Division 1. So Alice and Bob are playing a game on a binary string S of length n. Okay. Yeah. Only containing zeros and ones. Right. Alice moves first and the player takes alternate turns. In one turn, a player chooses a sequence of indices I1, I2 up until IM. Right, such that the characters at these positions form a non-increasing sequence and yeah, non-increasing sequence. Okay, and then the player then rearranges the characters at these positions in sorted order, right? And then the and yeah, formally let the chosen character consist of j zeros and zero the first yeah, the same thing they are saying, but they have specified one more strict condition that the number of zeros and the number of ones should be greater than or equals to one. Okay, and the first player who cannot make a move loses, right? So and then we just have to tell who the winner is going to be, and the constraints on n are the standard constraint, linear constraint, n is equals to 2e5. Okay, right? So yeah. So we are given some binary string. Okay, we are given some kind of binary string, and what operation a player can apply. So a player can choose any subset of indices let's say it chooses this index, it chooses this index, and then it chooses this index. The condition is the subset of indices that he chooses, that should form a non-increasing sequence. Okay, so and the number of zeros and number of ones should be greater than or equals to one. Okay, that should also be necessarily true, right? So yeah, so can I choose this subsequence? Yeah, I can, because this is a non-increasing subsequence and the number of ones and number of zeros are both greater than or equals to one. Okay, so yes, I after choosing this, what I can do is I can internally sort these indices. Okay, what do I mean by internally sort? I'll fix the rest of the elements as it is. Okay, and then from 110, what is going to be like the sorted sequence? It is going to be 011. So I'll place 0 here, 1 here, and 1 here. Okay, something like that, right? And then I just have to tell who is going to be my winner if they both play optimally. Okay, so if the string is already sorted, okay, so all the zeros are before ones. Okay, so if the string is already sorted, then obviously Alice cannot make a move, and so Bob wins by default. Okay, Bob wins, right? So if the string is not sorted, so if the string is not sorted, the claim is you can make the string sorted, in just one move. In just one move. This is the claim. Okay, and if and this would also be the most optimal for Alice. Why? Because since there always exists a one move way to make the string sorted, so if Alice doesn't sort it, Bob will. Okay, so and then if Bob will, then Alice would lose. So Alice would want to sort it in the first move itself. Okay, yeah. So so then comes how Alice is going to sort this sorted array. So this binary string. How Alice is going to sort this binary string? Okay. So one way to do is iterate through the characters. Okay, and if I find any occurrence of one. Okay, so let's say I come across this one. Okay, then I would just check in then I would just check that after this one if there exist any zeros. Okay, if there exist any zeros, I would take the rightmost zero. Okay, so I would, let's say, pick this zero. So I would pick this zero, and yeah, so for this one I'm going to pick this zero. Okay, yeah, so in my indices array I'll choose both of these indices. Okay, again, then I will move ahead. Let's say I found another one. Okay, so then I will check that if there exists some zero after this which has not already been picked, been picked, and I will choose that zero. Okay, right. So I will do something like this. A procedure like this is always going to yield me a sorted array. Okay. So let's look into the code for once to get more clarity. So here's the code. So I'm just taking the inputs and I'm saying that if S is already sorted, then the winner by default is Bob. Okay. Otherwise, the winner is always going to be Alice. How? So yeah. So the procedure I said, for that I'm using a set. Okay. So in set I'm inserting all the indices of the occurrences of the character 0, and then I am starting with so this is just my like set of indices of the operation. Okay, that is answer. Okay, so I'm starting with the first index. I am erasing all the occurrences, all the occurrences of 0 up until now. Okay, up until now like erasing all the occurrences of 0, right? And if the occurrence at this index, so at this index, if it is a 1, then I'm just checking if the size of my indices set is greater than 0. If it is, then I am inserting this into my answer. I am also inserting one occurrence of the 0 in my answer. Okay, and then I'm also erasing that occurrence of so like I'm also like erasing the index of that rightmost 0, okay, from my indices set. Okay, and yeah, and this is how I'm continuing. Okay, so I'll just attach the link to this submission. You can look from there. Okay, so let's discuss the complexity of this approach. So the overall complexity of this approach is, n log n, because I'm using a set, and space complexity is n. Okay, big of n. So yeah, that's that. Uh, let's move on to the next question. Okay, so let's read this question. We say that a bracket sequence A is better than a bracket sequence B. Okay, so if B is a prefix of A, but A is not equals to B, or let I be the first position if it exists where AI is not equals to BI. Okay, so like two regular bracket sequences are there, and we have to compare them. Which one is better than the other? So B is a prefix of A, but A is not equals to B. Okay, then A is better than B. Otherwise, if I is the first index where AI is not equals to BI, then AI should contain the starting bracket, and BI should have the ending bracket. Okay, right? And we are given a regular string S of even length, and among all non-empty subsequences of T, non-empty subsequences T of S that are regular bracket sequences, find the maximum possible length of T such that T is better than S. Okay, right? And the constraints on N again are linear. So, right. So, So first of all, what is a regular bracket sequence? A regular bracket sequence is that for every starting index, there is a corresponding ending. So every starting bracket, there is a corresponding ending bracket. Okay, so there is a kind of one-to-one mapping of this starting and ending bracket sequences. Okay, yeah, right. So we say that A is better than B. A is better than B if A is prefix of B. Wait. Sorry, B is a prefix of A, right? So if B is a prefix of A, is a prefix of A, and B is not equals to A, or the first index where I is different, bi has to be this, the closing bracket, and ai has to be this, the starting bracket. Okay. So yes, and then we are given a regular bracket S, regular bracket sequence S, okay, right? And we are given S, a regular bracket sequence, and then we have to find out the largest possible size of a subsequence T, which is better than A. Okay, we have to find T such that T is like maximum. Okay, and T is better than S. So first of all, let's look into the characteristics which makes T better than S. Okay. So obviously S cannot be a prefix of T. Cannot be a prefix of T. Why? Because T is a subsequence of S. Okay. T is a subsequence of S. Okay, so obviously the size of T is going to be less than size of S. So the first condition so the first way to make A better than B is never going to get satisfied. Okay, so if it is never going to get satisfied, how can I make the second one satisfy? Okay, so to make the second one satisfy, what I can do is, so I'll have to somehow find I'll have to somehow find a bracket sequence T. Okay, so at some index, which has at some index this character, and in SI there's a this character, and for all the previous characters till I minus one. Okay, SI is equals to TI. Okay, so yeah, right. So since they are going to be equal up until this index, and then in S there's a ending bracket, but in T there's an starting bracket. So what does that mean? So that means that I am skipping an ending character in S. Okay, so like while making T, I'll use till I minus one all the characters of S. Okay, they're exactly equals, but at the ith index there is some this character which I am going to skip, and then I move on to the some next character, right? And then I'm going to move on to the next character, which has to be this, which I'm going to put it here. Okay, right? Assume that here also it was this. Then I could have just made this. So in T also I could have just make it equals to like ending bracket, and then just I could just have move on. Okay, so yeah. So can you see something like this? So let's say my S is like this. Okay. So you would notice that again. So in T, I always need to have all these starting brackets, and in T, so in the next continuous subarray of ending brackets. Okay. So in that, I'm just going to check which is the last character. So which is the last ending bracket character. So if this is the last ending bracket character, then I am going to skip this one. Okay, why? Why can't I just skip this one? Because if I had to skip this one, then if I had to skip this one, then again I'll have to skip this one as well. So I'm skipping two characters to jump here. Okay, so that is going to impose a subset. So that is going to impose a more strict condition. Okay, like if there exists a validity or not. So that is going to impose a more stricter constraint. So Instead of doing that, I'm just going to take all the ending brackets, and I'm just going to skip the last ending bracket, and yeah, and then I'm going to choose this this starting bracket and so on. Okay, so is my task done? Like if I just skip this one and take the rest of them, is my task done? No. Why? Because t also should be regular. Okay, yeah. See, so among all non-empty subsequences T of S that are regular, so T also should be regular. So if T has to be regular, then from a regular bracket sequence, from an RBS, I removed what? An ending bracket, right? So now the number of starting brackets and the ending brackets are not same, not same. Okay. So then what I'm going to do is I'll also have to remove one starting bracket. Okay. But again, it may or may not lead to an RBS. That is what I have to check. Okay. So if I'm just removing this ending bracket, then can I remove one starting bracket as well after this, which makes my whole bracket sequence as RBS. Okay. So how am I going to check this? Obviously, I'm skipping this one and I'm definitely taking this one. So after this index, I have to find if there exists one starting bracket. Okay. So if there exists one such starting bracket, then I am going to skip that one as well. Okay. And it is definitely because because like if I denote my sum as number of starting brackets minus number of ending brackets. Okay, so in a RBS, every sum till ith index is greater than or equals to 0. Okay, this is a property of RBS. Okay, so if I am skipping a so if I am skipping an ending bracket, which means I am skipping a minus one, which means that my sum till here, so my sum, like after this index, all the sum over here has been incremented by one, right? So even if I remove this starting bracket, which contributes a plus one, okay. So if I'm skipping this, then it is not going to contribute plus one. So to all the indices over here, like it will get affected by minus one. So these plus one and minus one gets cancelled out. Okay. So what is my final condition? So my final condition is just that. So I start from the first index, and then uh, I am going to move until I find the first first sub array of ending brackets. Okay, so in that contiguous sub array of ending brackets, I will choose the last ending bracket to escape, and then I am just going to check if there exist two occurrences of starting bracket this. Okay, right? I just have to check that. Okay. So, like I skipped this one, then and since this was a contiguous subarray of ending brackets, then definitely this character is going to be my starting bracket. Like if the string doesn't end here, then yes. So automatically one occurrence has been found. I just have to find another occurrence. Okay. So yeah, this is what I have to done. This is what I have tried to done in my code. Okay. Like it's not the most optimal code, but yeah. So I'm starting with the first index I. So I'm starting with the first index. I'm iterating till I find one ending character. Okay, so this is what it condition does is, so whenever, so up until the ith character is a starting bracket, then I am just like moving on to the next index. Okay, right? So and then I'm trying to find the largest index j. I'm trying to find the largest index j for which s of j is a bracket, is an ending bracket. Okay, so now this j would correspond to which index? So this j would correspond to either so this j would correspond to what? So this j would correspond to my first uh, like so this j would correspond to an open bracket. Okay, after this contiguous subarray of ending brackets, this j would correspond to open brackets, right? That's why that's why this condition would have got false, and that's only when this while loop would have ended, right? So I have already found one occurrence of a starting bracket. Then I am starting with j plus 1th index, and then if I am checking that if there exists one occurrence of starting bracket or not. If there exists, then yes, I have found. And in this case, my answer is going to be n minus 2. Otherwise, my answer is always not possible. Okay. So like this can be a good proof work for you that like if there exists an answer, then there always exists a t of size n by n minus 2. Otherwise the answer is impossible. Okay. So yeah, that's that. So the overall complexity is big O of n, and the space complexity is also big O of n. Okay. Let's move on to the next question. So this is just a continuation of the previous question. It's just that in this question, the S given is not necessarily a bracket sequence. It can be any sequence of brackets. Okay, and yeah, and the definition of A being better than B is the same. We are defining some kind of a score. Okay, so this is how we are defining. So for an arbitrary bracket sequence T, we define its score in the following way. So if T is not a regular bracket sequence, then score is 0. Okay. If there exists a regular bracket sequence R of T such that R is better than T, then the score is equals to the maximum value of R over all subsequences of R. Otherwise, the score is 0. Okay. So, and then what we have to do, we are given a bracket sequence S of length and find the sum of the scores of all the non-empty subsequences of S. Okay. So for every non-empty subsequence of S, that is T, we have to we have to take the summation of the scores of T. Okay. And how is the score of T is being calculated? So if T is not a regular bracket sequence, the answer is directly equals to 0. Okay. If there exists a bracket sequence R such that R is better than T, then the score is equals to the maximum value of mod R over all subsequences of R. Otherwise, the score is 0. Okay. Yeah. So that's that. And what are the constraint on n? So n, so the constraint on n is 100. So this is important, right? So, so how have we defined a score of some string? Let's say t. Okay. So if t is not regular, t is not regular, 0. T is regular, and there exists a subsequence r of t. Okay, such that r is better than t. R is better than t. Again, so if t is regular, and if there exists a regular subsequence r of t such that r is also regular and which r is better than t, then this leads back to our previous question. Okay, so we can use the observations from our previous question into this question. How we are going to use it? So as I said, the condition to check if there exists an R of T such that R is better than T is just this. Uh, there there should be at least so so after the occurrence of this character, after the occurrence of first this character, which is an ending bracket. After the occurrence of the first subarray of this ending brackets, there should exist two. There should exist two opening brackets. Okay, that is that. And also, since this is going to be contiguous, so if I check for this bracket, if I check for this bracket, it doesn't really matter. Okay, so my final condition to check is this: there should exist. So there should exist a subsequence of this string. So in T there should exist an occurrence of this string as a subsequence in T. Okay, so this string should appear as a subsequence of T. Okay, and obviously T has to be regular. So if T is regular, and there exists this string as a subsequence of T, subsequence of T, then there exists an R. Okay, that's that's the only two condition I have to check, and if those two conditions are satisfied, that is T is regular and this appears. Okay, so this string appears as a subsequence in T. Okay, so this appears as a subsequence in T. Then what is going to be my score? So my score of T is going to be so my score of T is going to be the maximum size of some subsequence R which satisfies this condition. So, and as I told earlier, that maximum size is just going to be size of T minus 2. Okay, size of T minus 2. Okay, so we know beforehand, okay, what is going to be my score for any string. Okay, for any good string. So I'm stating, so if any string satisfies these two conditions, then uh, that string is going to be good. Okay. So my task has been transformed to count how many good strings are there. Count how many good strings are there. Good strings are there. Okay. So and if the size of the good string is, let's say, some x, then my score is going to be x minus 2, right? And since n is 100, can I formulate some kind of dp, some kind of dp, okay, which takes into which takes one, so which takes one state as this size of this string. Okay, so in my dp, if I put a state which denotes my size of the string, then how am I going to calculate my answer? So whatever this size is going to be, let's say if it is going to be I, then my answer is going to be I minus 2, right? So yeah, and then also I have to make this array, and I have to make this string as good. So to make an string good, I have to make it regular. Okay, and to make it regular, I'll have to and to make it regular, I also have to uh, I also have to maintain that for every prefix sum I, the sum has to be greater than or equals to 0, right? So I should also have one state which denotes that sum, right? Then comes the third thing. Okay, I also have to check that there exists an occurrence. So exists this string. So this string should appear as a subsequence entity. And to check this, sorry, this is not this. Yeah, so this string should appear as a subsequence in S, okay, or T rather. So to check this, I can maintain some kind of four size state. Okay, so an state with just size four. So zero would correspond to not getting like any occurrences of any of these. Okay, so that would correspond to zero. One would correspond to I have found this. Two would correspond to I have found this and this. Three would correspond to I have found this, and this. Okay, right. So yeah, so if I take another state, which just denotes like uh, what type of string is this? Okay, yeah. Then then that's all the information I need. Okay, so what is my no, final number? Final type of states are going to be there. So there has to be I, like till what index I am considering, till what index, till what index. Then there has to be sum. So what is my sum? So sum is just the sum of, and if I take this as minus one, then what is going to be my sum? So that is just sum. And then I also have to take the length. Okay, so what is the length of my substring? Yeah, so what is my length of the subsequence? And then going to be my type. Okay, so type can only be of four thing. Okay, 0, 1, 2, or 3. Okay, what can be the size of the length? So length can be from 0 to n. Okay, so this has the bound of n. What can be sum? Sum can also be from 0 to n. Why? Because I'm not allowed to take any negative sums. That would make my subsequences as not regular. Okay, I have to make a RBS as well. So to make RBS, I have to have all the sums between 0 to n, right? And then this is just my index, right? So which is also from 0 to n. So like how many total states are there? So for this is n, this is also n, this is also n, and this is just 4. So this is of the order of n cube. Okay, let's try to write the transitions. Okay, for the transitions, let's move on directly to the code. Okay, so that would be more clear, right? So this is a very descriptive code. You can get a very good idea like what I'm trying to do. Okay. So initially I have just declared this matrix of three dimensions. Okay. So I have removed the dimension of I. You can just replace like every like at every iteration you can just create a new DP matrix and then replace the previous DP matrix with this new DP matrix. Okay. So at every for every index I, what I'm doing is iterating through the length. I'm iterating through the length of the substring that I have got till now. Then I'm iterating through the sum. So what is my current sum? Okay, and then I'm iterating through the type. Okay, so if this is an ending bracket, and if the sum is exactly equals to zero, then I'm just continuing. Okay, what is going to be my new sum? So since this is an ending bracket, so my new sum is just going to be sum minus one. What is going to be my new type? Okay, so new type depends on what type do I have till now. Okay, so so let's discuss about the type. So as I said, so look here. So zero denotes that I haven't found any occurrence of any of this. Okay, one would denote that I have found my first, like I have found my ending bracket. Two would denote my I have found ending bracket and I have found one occurrence of my starting bracket. Three would denote that I have found ending bracket and I have found two occurrences of starting bracket. Okay. So if the ith character of so if my current character is my ending bracket, right? If my current character is an ending bracket, then I just need to check what I just so what is what can be my new type. So if it was zero, then it is going to be one. If it is one, it is going to be as remain as one. If it is two, then it is going to be two. If it is three, then it is going to be three. Okay. So this was my previous type, and this is going to be my new type. Okay. So this is what I have tried to do here. So I have initialized my new type as 1, and if my type is greater than or equals to new type, then my new type is again going to be as type. Okay, and then I am doing the and then I am just adding the number of strings from the previous state to my number of to the number of strings to this new state. Okay, length plus 1. Yeah, so this accounts for my take operation. So if I'm taking this character, what and and you can see that I have initialized with new dp is equals to dp. So this accounts for my not take thing. Okay, so if I'm not previous dp matrix, okay, and this accounts for my take operation. What if SI is an starting bracket? So if it is an starting bracket, then my new sum is just going to be sum plus 1, and my new type is 0. And yeah, and then again let's look into how my type is going to be changed. So type and new type. So if it is 0 and we get a starting bracket, then it is not going to affect at all. It is going to remain at 0. If it is 1 and we have got a starting bracket, then it goes to the new type 2. If it is 2 and then I have got another starting bracket, then it is going to be 3, and if it is 3 and I have got a starting bracket, then it is going to remain at 3. Okay, so let's look into what I have tried to done here. So if my type is equals to 1, then I am making my new type equals to 2. Otherwise, and if the type is greater than or equals to 2, then my new type is going to be equals to 3. Okay. And then again, I am just like accounting for take operation. Okay. So this is just a take not take DP. Here I have accounted for not take, and these transitions account for take. Okay. Yeah. And how am I going to calculate my final answer? So at the end, this DP matrix would denote what? So at the end, my DP matrix would just denote this. So like this DP matrix is just going to denote DP of n comma like everything. So this after the nth index. Okay. So I have considered it all the nth index. So what type of strings do I want? I want strings which has sum equals to 0. Right. And the way I have done my transitions, I just have to check my sum. Like if at any point of time the sum I is going less than 0, then I'm just not doing that transition, right? So the way that I have done my transitions, sum equals to 0 is always going to give me an RBS, regular bracket sequence. Okay. So I want sum is equals to 0, right? And I want type is equals to 3, right? And for every length I, whatever number of like subsequences are there with sum is equals to 0 and type is equals to 3, it would contribute I minus 2 to my answer. Okay. So this is what I have tried to done here. So I'm iterating through the lens. I'm iterating through the lens. Okay. And then I'm just adding dp of I of sum is equals to 0 and type is equals to 3 and I is just my length into like what answer does it contribute to my final answer. So it contributes I minus 2 to my final answer and that's that. Yeah. So the overall time complexity is, so the time complexity is big of n cube, like the number of states are n cube and the complexity is also like the like to do one to do the transition is also like a constant time. Okay, big of one. So that's why the overall time complexity is O of n cube and the space complexity is also O of n cube, big of n cube. Not exactly big of n cube, it is big of n square. If you go by my implementation, it is just big of n square because I have removed one state of index. Okay, like even if you had included it in your DP matrix, it would have passed. But yeah, for my code, the space complexity is big of n square. Let's quickly move on to the next question. Okay, so yeah, so let's read this question. So this is an interactive problem. This is Div1 C and it is Div1's E. Okay. So this is an interactive problem for a permutation G defines reverse and we there is a hidden permutation P of size n. We have to find the lexicographically smallest permutation Q of size n such that Q is greater than P and reverse of Q is greater than reverse of P. However, we do not need to output the Q itself. Instead, we must output a permutation R of the indices. Okay. So we just have to output a permutation of the indices of the original permutation P. Okay. And we have to do this in maximum of 3n queries and we also have to tell that if no such permutation exists. Okay. So whatever my hidden permutation is, like it always makes sense to alter the rightmost kind of like a kind of my rightmost element, right? We want to find the Q which is lexicographically smallest. Okay. So out of all the permutations which satisfies the conditions, I have to output the permutation which is lexicographically smallest, right? So, and obviously Q is greater than P. So, till some index I, my Pi is going to be equals to Qi, right? And then there exists some index I plus 1 for which Pi plus 1 is less than Qi plus 1, right? And then after that, I can alter the permutation however I would like. Okay, as long as reverse of Q is also greater than or equals also greater than reverse of P, right? As long as this is satisfied and this is satisfied, I just have to output the lexicographically smallest permutation. Okay, so I want the so let's look into some example like 1 3 2 4. Okay, 1 3 2 4. Can I bring 2 over here and can I bring 3 over here? Okay. So what is going to be look like? This is going to look like this. So in this as well, Q is greater than P and reverse of Q is greater than reverse of P. Okay. But is this the lexicographically smallest one? Like I have altered at the first position itself. Okay. So let's try to fix this first position. So let's try to fix one right there. Okay. So if I fix my one right over there, okay. So in Q as well, and so this is P. So in Q, and then if I want to change this one, then I'll have to put 4 over here, right? But then it is not actually possible because whatever element that comes over here, like 3 or 2, it is going to be smaller than 4. So it is not actually possible, right? Let's take some other example, like 1, 3, 2, 5, 4. So yeah, let's try to let's try to go back in reverse. Okay, so if like how like if I can make I number of elements fix in Q, like first I elements in fix in Q, then I would want to make it I would want to fix them. Why? Because it is always going to lead me to a lexicographically smaller. So if I fix I minus one elements and if I fix I elements, this permutation is always going to be lexicographically smaller than this permutation, right? So that's why I would want to fix as many more elements as possible. Okay, so let's say I have fixed these two elements over here. Okay, and let's say I want to make, so yeah, and over here I want to change this element. So I would want to put 4 over here, right? So like 1, 3, 4, and then I would put my 2 over here and 5 over here. So yeah, this leads to my lexicographically smallest one. Can I fix 2 as well? Can I fix 2 as well? So if I am fixing 2, then I cannot replace 5 with a larger number, so it is not possible, right? Right? Let's say something like this: 1, 5, 4, 3, 2. Let's say this is my array. This is my array. Then can I fix these three elements? Or can I fix just these two elements? Okay. So if I'm fixing these two elements, then I would want to replace 4 with a larger number, but there doesn't exist any larger number in the suffix. So it is not possible. Can I fix just one? So if I'm fixing just one, then I would want to replace 5 with a larger number in its suffix, but there doesn't exist any such larger number. Then in that case, I'll have to change the one itself. So I would want to replace one with the larger number in its suffix. So I would want to choose the smallest one of them, that is 2, right? So I would I would replace 2 with 1, and then what I'm left with? I'm left with 1, 5, 4, and 3. Okay. With that, I want to calculate the lexicographically smallest array, lexicographically smallest uh, permutation, like which is also larger than the original one in its reverse as well. Okay, so for that to happen, for that to happen, I'll have to put some element over here which is greater than 2, right? So obviously I can't put 1 over there, but I can put 4 or 5. I also want to make lexicographically smaller, so I would put 5, then I would put 4 over here, then I would put 3 over here, and then I put 1 over here, and this is just going to be my 2. So my claim is, so my claim, you can also see that the first index which is going to get altered, after that after that I can just output my sorted list of numbers. Okay, So the first index, so the ith index at which I am altering, so at which I am, so at which pi is not equals to qi. Okay, so at that index, I am going to put an qi which is greater than pi, but after that, from I plus 1 till n, I'll just sort the indices. Okay, and it is always going to lead me to what? It is always going to lead me to a permutation whose reverse is larger than my original permutation. Okay, but I can't I can't choose any such I. Okay, I'll have to choose. Okay, so I'll have to choose an element I. I'll have to choose an element I which has some element greater than. I'll have to choose an element which I have to choose index I which has some element greater than it. Okay, so if it has at least one element greater than it in its suffix, then I can choose this element. Okay, right? So again, the claim is that I is the first index, I is the fund. So like if you come from reverse and the elements are like this, it is first decreasing and then increasing. Okay, so my claim is I is the first element. This increasing sequence, the first element which is smaller than this peak. So whatever this peak is, the first element which is smaller than this can be my I. Okay, right, right. Yeah. So how did I come to this conclusion? So I come to this conclusion first. So let's say there is no decreasing sequence. Okay, there's only this increasing sequence. So this increasing sequence. So this increase. So if this is an increasing sequence and I have got an element over here which is smaller than this element. So what I can do is I can replace this element with the smallest element which is greater than this, the smallest element which is greater than this, and then I can just sort the rest of the elements, and it is guaranteed that this array is going to be uh, the reverse of this permutation is going to be larger than the reverse of the original permutation. Okay. And since I have replaced this element with an element larger than this, the P is greater than, like Q is greater than P condition is also satisfied. Right. Right. Why can't I choose some element in between this increasing sequence? So I can't, like it is obvious. So if I choose this element, there doesn't exist any element which is greater than this element. Okay. So I can't choose that. So the first element I for which pi is less than pi plus 1, I can choose that. Okay. So in this case, I can choose this element, but I has to be less than or equals to n minus 2. So if I is one base, okay, then I has to be less than or equals to n minus 2, right? What if what if my largest element, like what if my last element and the second last element, it is like this, okay, so this is greater than this, then what happens? Then again, this is the case of this thing over here. Okay, this thing over here, right? So it is not that easy. So the final solution is just this. So there would be some sequence of decreasing sequence, then there would be some increasing sequence, and then there would be this element. Okay, so then I would find the element, then I would find the element which is just greater, which is the like the smallest element which is greater than this element in whole of this suffix, then I am going to replace it with that, and then I am going to replace all these elements. Then I am going to replace um all these elements with the like the sorted sequence. Okay, and it is guaranteed that uh, this this like this suffix is always going to lead to a permutation which makes reverse of q greater than reverse of p. Okay, so my solution so what do we have to do? Okay, so to arrive at this element I would need order of n queries. Order of n queries. In that number of queries I can arrive at this first element which satisfies these conditions, right? Like there is first a decreasing sequence, then there is a increasing sequence. So to arrive at this I would need at most n number of operations. Okay, and to identify this and to identify this decreasing sequence and this increasing sequence can also be done using this n operations only. Like I don't have to use any extra operations. While doing this operation I can also make two vectors which first denotes this decreasing sequence and then this increasing sequence. That can be done in that n number of operations only, right? And the thing I would replace them with the sorted with the how do I say it, like the sorted vector. Okay, so to replace two monotonic vectors with a merged monotonic vector, how many operations do I need? I need big O of, like I need at most n plus m. Okay, like n1 plus m1. Okay, so n1 plus m1 is here obviously is less than n. Okay, so to merge these two monotonic vectors I would need another n operations, right? And in this merged monotonic vector I am also going to find the smallest element which is larger than my pi, the smallest element x which is larger than my pi, that is again going to that would again require me like at most n operations. So so the first is to arrive at that index I, arrive at that index I, n operations, then merge the two sequences. That is again going to take me at most n operations, and then find x, smallest x which is greater than pi. That is again going to take me n operations. So overall this is 3 n operations which is acceptable. Okay, let's look into the code. So I have just write a query function. Okay, right. So initially I'm just trying to find out the starting index of my increasing sequence. Okay, when I say the increasing sequence I mean this. So as I said, so like I index is over here, this is my, so like this. So I like my perspective is from the back. Okay, so through my perspective this is a decreasing sequence and this is an increasing sequence. Okay, so I'm trying to find out this index, the starting index of this increasing sequence. Okay, so I'm trying to just find out the starting index of this increasing sequence. Okay, so all the elements which do not belong to this increasing sequence, that is going to belong to the increasing sequence, sorry, the decreasing sequence. Okay, so in st I am including all the elements of the increasing sequence, and res, I am including all the elements of the decreasing sequence. Okay, so let's say I have found that index. Okay, so let's say I have found that jth index, then I am querying. Then I am trying to find out the index I. Okay, so the in my solution, the whatever index, so I was denoting this element as my index I. So I am trying to find out. So this is my ith element over here, and this element is greater than this. So this index I am trying to find this index I. Okay, so this is going to be true when it is going to be true when my query for j comma the last element is 1. So if that query is 1, then only my then I have found my index I. Otherwise, what I am going to do is I am just going to append this jth index into my increasing sequence, and then I'm just decrementing my j. Okay, so like what if I have found? So if I have found, then I'm trying to construct my answer. Okay, so to construct my answer, obviously I'm going to take all the elements so all the indices less than I, all indices like pro uh, I'm going to take 1 2 till and I minus 1. I'm going to take them as it is. Okay, and then I'm trying to construct my merged vector. Okay, merged monotonic vector. I'm trying to construct them. Okay, so this whole code over here is I have written to merge the uh, right, and finally I have got this monotonic vector, and again to merge this as well I am going to require order of n number of queries. Okay, so in this merged vector I am going to I also need to find the smallest element which is greater than my ith element. Okay, so this j denotes my ith element, that is pi, the first element which I am changing. Okay, so to do that I'll have to, yeah, so I have found this. So the element that I have found, then again then I am replacing that ith element with this x. Okay, with this x. Okay, so the smallest x which is greater than my pi. So I am replacing that with my this is the smallest x. Okay, and then I am going to then I am going to like append all the rest of the indices. Okay, so if k is equals to I, then only I am going to append my j. Otherwise, it is going to be my same as the my merged sequence of sorted indices. Okay, like sorted elements, and then I'm just printing my answer. Okay, so that's that. Uh, like the overall time complexity is big of n, number of queries required is 3n, right? And the space complexity is also big of n, right? I hope you I hope you like the discussion. Uh, so I hope you like the discussion. So yeah.